All right, so in this video, we're going to take a look back at some big ideas in terms of solving equations, so we could use those with the new content we've got. And then we're also going to look maybe a little bit too far ahead, but we're going to look ahead and try to take a look at what is out there besides what you've already learned in terms of these things called roots, which we'll talk about shortly. So first of all, big picture, we solved equations. We've been solving a lot of equations in this class. And for as much as there's different types of equations that ask you to do different numbers of steps and different steps, there's only two really big things that we have to keep an eye on to make sure we're doing a nice job with this. First thing is we have to know that simplifying or rewriting either one or both sides so that they're more manageable is perfectly legal as long as you write an equivalent expression when you change the way the side looks. So looking at the equation I'm going to use to talk me through this, the left-hand side seems like I could probably rewrite that a different way. And if I chose to do that and I wrote an equivalent expression for 1/2 times the quantity 6x plus 4, then my new equation would be equivalent to what I was given from the beginning. So rewriting one side or the other, perfectly legal. Let's go through that. We'll distribute the 1/2. A half of 6x is 3x. A half of 4 is 2, leaving me with that. And the right-hand side, since 1/2 of 6x plus 4 was equal to 3/2 x, then we can be sure that this other version of that is equal to 3/2 x also. So we have an equivalent equation. So equivalent expressions, equivalent equations, it's a good way to work equations. Now, our main goal when we're solving an equation is to try to figure out what value of x made this relationship true. We were given an equation that was true for some unknown value of x. And our goal is to tell people, well, if you use x equals blank, then this equation was going to be true. So we're not there yet because we don't have x by itself. So the other thing we can do is we can perform balanced inverse operations to write equivalent equations that get closer and closer and closer to having x by itself. So equivalent equations that are simpler to work with. So looking at this thing here, I have x's on both sides, which we're going to have to tackle at some point, but I think there's enough people that are worried about fractions that maybe I want to choose an inverse operation to eliminate the fraction. Every time you do something in an equation, you've got a reason for it. In this case, I want to get rid of the divided by 2 that's causing the fraction. So I think my inverse operation would be times 2. If I multiply both sides of the equation by 2, I'll get a new equation. And what's on each side of the equation, it's not what we had before. 3x plus 2 is not the same as 6x plus 4. But because I multiplied both sides of the equation by 2, I'll get an equivalent equation with different expressions in it. And I'll do the same thing here, where if I'm trying to get closer and closer to having x by itself, I now have an easier time figuring out which side of the equation I want to bring x's to. I'm not intimidated by this 3/2 x anymore. So I would probably choose to subtract 6x's from both sides. Again, a balanced operation, subtracting on both sides, and an inverse operation for something I wanted to change. I didn't want to have x's on both sides, so this positive 6x, I used the inverse operation, subtracting 6x. Did it on both sides, got a new equivalent equation, which is even closer to having x by itself. The only thing keeping it from having x by itself is this -3 times. So again, you choose an inverse operation for -3 times, which is divided by -3, and you find out what x would be. Okay, so that's the big idea for solving equations, which we'll apply to all the algebra you've been learning recently. But before we do that, let's talk about something we're going to have to do. The inverse operations that we're going to have to use are going to introduce, or they're going to include an operation you might not even think of as an operation yet. You've seen this expression before. If I asked anyone what it was, someone might say it's a square root symbol. And the truth of the matter is it's a little bit more than that, but it's a good place to start. It's called a radical sign. And the first time it's introduced as this new thing called a square root. And the way you've seen it is probably something like this. They usually start off with some nice tame questions where they say, let's tell you what square root means by saying, when we take the square root of 25, we ask the question, what number times itself makes 25? So it's a pretty weird thing where it's not times, it's not plus, it's not minus, but it's related to those things. It's a pretty complex question. What number times itself makes 25? Ultimately, you start getting comfortable with when you see a 25 underneath the square root symbol, when you see a 49, which we know is 7 times 7, when you see an 81, which is 9 times 9, you start thinking that square roots maybe aren't the worst thing in the world. Square root of 25 is 5. One trap that I see students fall into a lot of times is square root of an even number is sometimes something that people will slip up on. And it's usually careless early on. Sometimes it's lack of understanding early on. But what number times itself makes 16, because 16 is even, it's pretty easy for a student to say it's 8. But the fact of the matter is it's 4. It's 4 times itself gets you 16. It's not 8, so just be careful for that. When you're taking the square root of an even number, I don't want you thinking divided by 2. So what's going to be new about this then? First of all, I need you to understand that a square root is an operation. So as I mentioned before, it's not your add, subtract, multiply, divide. It's a pretty loaded operation because it gives you that what times itself makes what, 2 copies of something. So it's a weird operation like that, but it's an operation. It's an operation we can use as an inverse operation somewhere down the line. That's one thing. And the other thing is, if radical is more than just a square root, I need to at least mention that this radical can be used to represent a lot of operations, not just square root, just generally roots. And that's because sometimes you'll see this radical symbol. I'm going to stop calling it a square root now. A radical symbol with a little number up there called an index. For example, you might see this. So what does that do for us? Well, if you just looked at the square, if you thought of this as just the square root of 27 would be a pretty tricky question, because the square root of 25 is 5, and then the next perfect square I know of is 36, so the square root of 36 would be comfortable. Square root of 27 is stuck in the middle, but this is not actually a square root. This is what's called a cube root. And a cube root is asking a similar question to square root, but it's asking what number is there for which 3 copies multiplied together makes 27. So it's not what times itself gets 27, it's what times itself times itself. So that's off of our times tables. We don't think of times tables as 3 things getting multiplied together. So you have to get a little bit of work with it, kind of play with numbers a little bit. Well, we think of 27 like this, but then isn't 27, if it's 3 times 9, isn't also 3 times 3 times 3? So I guess then the cube root of 27 is 3. So over your careers, more in Algebra 2 than anything, you'll see cube roots. The last thing I want to say here, again, is more of an Algebra 2 introduction. It's not something you'll use as we go to solve equations, but roots are also expressed using fractional exponents. And fractional exponents, let's give you some examples of what we're talking about. Our experience with exponents has been this. We know about a number, and we know what it means to square a number. And we know what it means to cube a number. 3 times 3 times 3 would get you to 27. Very closely related to what we just did, by the way. We have, even in this class, gone so far as to say what a number to the 0 power might be. 3 to the 0, just like anything to the 0 power, is 1. And if you remember, we even went so far as to say what a negative exponent might be, but we were only talking integers. So -1 as an exponent, we decided, instead of multiplying in extra copies of 3, it was the opposite. We figured it was dividing out a 3. So it was starting here and dividing out a 3, a fraction appeared. So negative exponents were tied to fractions. But what about fractional exponents? Well, there are fractional exponents. They do exist. They do have applications, some pretty important ones, honestly. But what a square root and a fractional exponent have to do with one another, I hope I can make that clear in the last minute or so, or even a cube root and a 1/3 power. So the idea is here, to introduce this, let's talk about a bigger number, which would be easier to look at pieces of. So 64. If we were talking about squaring 64, that's a big number, and it's probably about the biggest I would want to write. So if I was going 64 to the 3rd, I might just write that instead. But working backwards off of that, well, let's get those out of the way first. Working backwards off of that, x to the 1/2 power, in this case 64 to the 1/2 power, is saying I'm thinking of 64. I'm thinking about breaking it into 2 equal pieces. But it's not dividing it. It's what 2 equal pieces multiplied together makes 64. Say that again. What 2 equal pieces multiplied together makes 64. So it's not multiple copies of 64 multiplied one after the other after the other. It's a partial copy of 64 multiplied together to make 64. So 2 things that multiply together to make 64 is actually the same question as we would have asked if we were doing square root. So as it turns out, a fractional exponent, x to the 1/2 power, means the square root. So 64 to the 1/2 power means the square root of 64, that means 8. And the cube root, which we were introduced to earlier in this video, that would be represented as x to the 1/3 power. And once again, cube root, something that you're not going to see a whole lot of. If we were trying to do that with 64, we'd probably have to play with 64 a little bit, think about different ways it's written. And eventually you stumble on the fact that 64 could be made up of 3 copies of 4 multiplied together. So the cube root of 64 is 4. And 64 to the 1/3 power, because they mean the same thing, is also 4. The one last piece here is this, going back to those missing pieces in the table there, don't worry, because we know there's no even number, no integer number times itself gets you 3. So a lot of times people would just leave it like this and say, think about the number. It's probably it's a never ending decimal called an irrational number. But if you come across situations like that, you'll be allowed to leave it like this. Kind of like we just left fractions. 7 doesn't divide nicely by 3, so we'll call it 7/3. Well, I can't think of a nice equal number, or integer number that multiplies by itself to get 3. So let's just describe it as the square root of 3. So there's a lot to take in. Let's see what we really need to take away from here. We used inverse operations and equivalent expressions to solve equations. And then this idea of a radical, it's going to be an operation we're going to use in the next video to actually perform a job.